So we have discussed integral method of analysis, which is a means of guessing and testing the appropriate rate law or rate expression that would go with or that will represent the given empirical set of data. So if what we have guessed is not appropriate or is not correct, then we will have another guess and test that particular guess. So in this particular method of guessing and testing, you've learned that this will only be applying for simple reaction types corresponding to what we call elementary reactions. Now, if you recall also that in the case of the second order reaction and the third order reaction, we have the case 3 for both types of reactions, in which we are now talking about non-elementary reactions. The other two cases for these two types of reactions are elementary, whereas the third case for both the second order and the third order are all non-elementary. So as a review, so we have learned how to derive, we have learned how to derive from this particular differential equation, this particular formula that will allow us to interpret the reactor data given the concentration versus time data, set of data for your particular reaction. So if it's not concentration and time that is given you, if it's conversion and time, you have this alternative formula that you can use. So if the plot of your experimental data will not form a straight line based on the two formulas just presented, including this one, you have to guess another type of reaction for your particular type of set of empirical data. Because that is the case, if the set of empirical data is not a straight line for these two equations, then what you guessed is wrong, that your reaction is first order, irreversible, unimolecular. So it's wrong, then you have to make another guess for that matter. Now, you can also have a second order bimolecular type of reaction in which you have a case 1, the case in which you have two species, and that your differential equation could be written in this manner. And your rate law will be negative RA or negative RB being equal to KCACB, okay, in both cases. Now for this, the amounts of A and B reacted at any time are said to be equal. Now I have presented to you the amounts of A and B representation. Based on my memory can still serve me right, I asked Jabime to represent a particular part of A and B that has reacted after a certain time. Now, can anybody here share what is the representation for the amount of A and B that has reacted after some time? Because it's very important and that's very fundamental in the understanding of problems that you will encounter later on. How do we represent the amount of A and B that has reacted after some time? Anyone? How do we represent the amounts of A and B reacted after some time? John Vincent Rivera, how do we represent it? John, are you there?
Hello.
Yes. How do we represent the amounts of A and B that has reacted after some time? So we're doing a review before we go to our next lesson.
It's probably means na the amount of A or B that reacted is just equal to the amount of A or B that has disappeared, miss.
That has
That's what
disappeared.
would be.
Yeah, you're correct. The amount of A and B that has reacted is the same amount of A and B that has disappeared due to the reaction. What I'm asking, Jen, is how would you represent it in differential equation? In here, if you'd like to solve a problem, how will you represent it? Okay, I'll show my whiteboard. How would I write it? The amount of A and B reacted, how is it written? You can dictate to me. How will I write the amount of A and B that has reacted?
I'm not really sure, Miss, but is it
Okay.
negative the negative differential of the amount of A over time?
No, amount of A and B that has reacted. Jabi May. So it was Jabi May who I asked last meeting, and she was able to uh, give the correct answer. Jabi May, can you refresh the class on what is the proper representation of,
Miss,
yes,
Miss.
yes,
Ang CaOXA to, di ba, Miss?
CaOXA and
Miss.
CbOXB.
CaOXA.
Okay, so that's it. Okay, so John and the rest of the John in the room. So this is how we represent the amount of A that has reacted or disappeared, the amount of B that has reacted or disappeared. So that's important. This is a very fundamental concept in kinetics, that you know how to properly represent the amount of A and B, or the amount of any species for that matter that has reacted. So I'll go back to my slide. Okay, so this is for case one, and we arrive at this particular different representations, and it's part of your problem set, which I already placed on Canvas. You are to derive how this particular formula came from this. Now, we have discussed that this formula came from the process of separation of variables, and the integration process is a method of partial fractions. So you have to do that. That way you will arrive at these particular expressions that you have here for case one. And in here, you will have a corresponding set of data that you will need to plot. And then again, you test that particular set of data, whether the plot will be a straight line based on these particular options that you have, depending on the given in the problem. So it's either this that you will plot against time, or this against time, or this against time. If you have a reasonable straight line, when I say reasonable, probably your R value for your best fit line is around 0.98 or 0.95. That's reasonable enough. Then your guess is already acceptable. That it's a second order reaction, case one. Okay. Now, if it's really very far from that, then you have to guess another rate order of reaction or rate expression that you will again check the plot of your data with. Now, these are things that we also have discussed, that whenever one of the species in your second order reaction has an initial concentration which is too big, that whenever a portion of the other species in which it's reacting with reacts with it, we say that there's very minimal or negligible amount that has disappeared from this particular species, which is very large in value, saying that the rate of reaction is independent of the concentration of this species. If the rate of the reaction is independent to the concentration of this species, then our reaction is said to be a pseudo first order reaction, or we say sa atong lingwahe, daw first order lang siya, because the rate is not anymore affected by the changes in the concentration of that species which is present in very large concentration. Okay, now we also have case two for second order reaction, in which you have only one species but two moles of that species forming the product, and you have a different rate law for that in this case, and you will have a different equation relating concentration to time or conversion to time. So it's either this equated to KT or this expression equated to KT. There's a need for you to linearize as well the equation that are provided. So you have two options, either this one and this linearize, or this one with this linearize. Then you have to test the fit again of your experimental data. Okay. In the case of the plotting that you will do, so you have something, you have two options here, 1 over CA or XA over 1 minus XA versus time that you will also plot. Now, for case 3, this is the one that I said that the stoichiometry does not anymore agree with the rate law. So it's first order with respect to A and B. Hence, there is no agreement between stoichiometry and the rate law. That is the case, you will have it represented like this. And you will have this expression for CA and CB changed to this one. I have already shown to you how the derivation is done. And after separation of variables and method of partial fractions in integration, you will have these formulas you will arrive at. Okay, in terms of the second order irreversible reaction, non-elementary in the case of case 3. Now, we can also have trimolecular or thermolecular irreversible third order type of reaction. You have 3 species here, and you have the rate law here. You have the differential equation here. You can change the dCA dt to dXA dt and CaO representation. You have to, there's a need for you to express the other concentration in terms of just one concentration, or in this case, it's in terms of conversion. We change the C sub A in terms of conversion. Now, you cannot process the DE if you have a variable XA here and the rest here is still CA, CB, and CD. So there's a need for you to convert these concentrations in terms of conversion of A. And this is the way it's converted, and the rest would be your math. You separate variables and you use method of partial fractions, yielding this particular formula for the first case under third order irreversible type of reaction. Now, the same premise or the same principle applies here, that if one species is, in terms of initial concentration, is very large compared to the other two, your reaction becomes pseudo second order, meaning the rate of reaction is not affected by changes in the concentration of that particular species. Okay, now we have case 2, and this is the most common type. You have a mole of one species reacting with 2 moles of another, and this will be your rate law based on the stoichiometry. By the way, both case 1 and case 2 are interpreted as elementary reactions. This is again the corresponding equivalent of this differential equation, changing C sub A in terms of X sub A. And we still have M representing the ratio of the initial concentration of B to A, just like in second order reaction. And this will be your corresponding answer to the method of partial fractions after separation of variables. So this is for m not equal to 2, and this is for m equal to 2. Okay. The third case is non-elementary because stoichiometry does not agree with the rate law in this case. And we proceed just like what we did with the other cases that we have discussed for other types of reaction. And this is our answer. So this is your 1 over Ca squared minus 1 over CaO squared equal to 2 kT if m is equal to 1. If m is not equal to 1, meaning if it's in any other value other than 1, this will be your formula for this case 3. So in here, including the zero order reaction, I think we ended with the zero order reaction in which the rate is not dependent on concentration. So it's dependent on concentration. Wait. So there are other things in which the rate of the reaction is dependent on. Those things that were mentioned by Levenspiel I placed in here. So it could be in terms of light intensity or intensity of radiation, and the presence of catalyst and the surface available for reaction in the case of solid catalyzed gas reactions, as those examples for zero order reactions. So for zero order reaction, the rate law is something like this. You don't see a, why is it that I don't see anything here? Wait, class. So this is, let me just open it in here. So this is it. So for zero order reaction, you don't have the concentration term appearing on the right side. So you have a very simple differential equation to deal with, and this will be your corresponding formula. For the t provided in the problem, which is less than CaO over K, this will be the formula that you will use. If the t that is provided in the problem has a value already equal to or greater than CaO over K, automatically the C sub A that you will answer is 0. Now you may wonder why you have two sets of formulas for the case of zero order reaction. One formula is for T less than CaO over K, and the other one is for value greater or equal to CaO over K. Because there are problems later on which are zero order, stated in the problem, wherein after some time, after the time that is specified in the problem, let's say for example after an hour, you'll be solving for Ca based on the formula that you have here. You will wonder why the Ca value that you got is already negative. So it's not unacceptable. So if you will validate your answer, there's no negative sign for the concentration. So what does that mean or imply in that case wherein the computed C sub A you got out of the first formula that you have here on top is negative? It's because at that time that is given in the problem in which you are to determine the remaining amount of Ca or the remaining amount of A, that is, the A is already completely consumed. That is why your computed value is negative. So I am suggesting that in the case of zero order reaction, if it's already specified in the problem, you have to check first based on the T that you are to determine, let's say the conversion or the concentration. Check first whether the value of the T that is provided is less than the initial concentration and the rate constant that is provided. Or otherwise, if its value is greater or equal to CaO over K, there's no need for you to compute anymore. Automatically, you can answer that there's no A left based on the time that is given in the problem. But if the time that is given in the problem in which you are to determine the concentration of A left or the conversion of A is less than the initial concentration divided by K, then you are to really determine the Ca or the Xa based on this formula. Otherwise, there's no need for you to compute, because if you will compute based on this formula, as I have said, the answer that you will be getting is negative, telling you that A is already completely consumed or is 100% converted to the product or products of reaction. So this one is only true for zero order reaction. So for other reactions, you only have one particular formula for a particular case, or one particular formula for, let's say, for a first order reaction. It's only for this one. Okay, so this is where we ended last meeting. So we have allotted 30 minutes for this. That way, everybody now have a complete recollection of what we have discussed last meeting. Okay, so now for this afternoon, we are actually going to determine the value of the order of the reaction and the rate constant directly on the interpreted differential equation. Although class the process is a trial and error process, but the thing is you're not guessing and testing and plotting at the same time. In here, you may have a guess and you test, but there's no need for you to check the plot of your data if whether it's a straight line. You are going to guess directly a value for the n, and after you have already determined the value of the n, or you're satisfied with the value of the n, that's the time that you determine the rate constant. So this is also actually guesswork because may trial and error siyang apart, but the thing is there's no need for you to plot. But nonetheless, there's no other method to determine the n other than these two in which you can directly solve for it. Especially if you're given when we talk about integral method of analysis. So before I go to this one, the methods of determining the n and k, I will share the chapter and problems of Levin's field so we can practice solving based on what we have discussed last meeting on the four types of reaction: the zero, the first order, the second order, and the third order types of reaction. So we'll go to Levenspiel. Okay, wait, class. I cannot find it. Wait. Here it is. So we'll pick some of the problems here that will illustrate or will check your understanding on the topics that we have discussed before we go to the next part in the lesson, which is determining N and K empiric based on the set of data, not with plotting anymore, but rather directly testing it based on the equation, the differential equation. Now, in here in 3.1, you're given that the rate is zero point 0.2 moles per liter per second when the initial concentration is 1 mole per liter. What is the rate of reaction when Ca is equal to 10 moles per liter? So there's a note here that the order of the reaction is not given. Okay, the order of the reaction is not given in this case. So if you're going to write down, I'll just annotate here directly. You have the rate, this one, and the corresponding Ca. So there's a pair of data that you have, the rate, which is zero point 0.2 mole per liter second, and you have the corresponding concentration, 1 mole per liter. Then you have this question already. What is the rate of the reaction? So meaning, let's say if we'll have this as Ra sub 1, and this is C sub A1. This is your first set of data. So the requirement is asking you for the rate. So I will have it labeled as R sub A2 when the concentration this time is 10 moles per liter. Okay. Now, the order of the reaction is not given. So how will you solve this particular problem? Or how will you find what is being asked, which is the rate at the concentration of 10 moles per liter? Okay, let us go to the whiteboard. You're given rate 1. You have a value there, and Ca1 for 1 mole per liter. And you have rate 2, unknown, for a Ca value of 10 moles per liter. Okay? The order of the reaction, N, is not given. So there are things in which Levenspiel is really asking questions that will test your understanding on a particular principle. So in here, 0.2 mole per liter. So I'll go back. So this is 0.2 mole per liter per second. Okay, so anyone here who can tell us what would be the route or what would be the proper way of determining the unknown in this particular problem? Or if I may say, can we really determine the required information in this case? The order of the reaction is not given. So let's say, for example, if it's not given, so I will guide you. If we'll have to start with the solution and the order is not given, how would you write the rate law that will represent the given reaction? If I will ask, write the rate law for the reaction given the set of data that is provided here without the order of the reaction, how would you write it down? Joanna, how would you write down the rate law, Joanna?
Good afternoon, Miss.
Good afternoon.
If ako, Miss, sige, Miss, ang usual na balang, ang first order na, do, Ani ko siya duma-assume nga amo na anay ang aton nga order sang reaction which is ang negative RA is equal to uh, KCA amo na means KCA1
Okay.
ang normal.
So in your case, you're saying that we will assume that this is a first order reaction, right?
Miss.
Okay, sige.
Amo na nga
You
confirm.
you are suggesting that we will assume that this is a first order reaction.
Oo.
Okay. But the thing is, Joanna, are we provided with a set of empirical data to test?
Ay, wala, miss.
O wala. So muna gani, if you're not provided with a set of empirical data to test, then you cannot perform what we have discussed last time, that in which you have to guess and test. Like what you said, I will guess that this is first order. I will look for the appropriate equation that I will use to plot my empirical data. In our case, we cannot plot because if you're going to plot, we only have a point, right? Isa lang kaset. So how can we determine what we want to determine, or how can we validate, rather not determine, how can we validate that our guess is correct if we're only provided with one data? So in this case, what you're going to do, I will suggest is, since you do not know the order, you write N. Okay? You do not know
Okay,
the
okay,
order
miss.
because the reaction order and the rate constant is not given in the problem. But we know, okay, thank you, Joanna. But
Okay, miss.
we know that for any reaction, whatever is the set of data, the order and the K should be the same. What do I mean by that? If I have 10 pairs of RA and CA, and I have already determined the order and the K, whichever of those 10 pairs of information or empirical data I will use, I should arrive at the same K and N. It should not change because we're talking of the same reaction. So it's the same thing with this. So if I'm going to use that information, then for the second here, for the second set or pair of data, the rate constant should be the same, even though I do not know the order of the reaction. So in that case, I will write here the rate constant. Now, if I will use the data, the first set of data would be the rate divided by the C sub A1 raised to N. Now, you may ask, how can we solve for the actual when we don't have the N? Then don't solve for the actual. You just give the value of RA. You just rather substitute the values that are available. So you have a 0.2, right? And you have a 1 raised to N. That's the K. I have this as equation 1. That's my K based on the second data, set of data. Remember that the K in here and this K must be the same. So if I write a new rate expression, RA2, and that would be K CA2 raised to N, this K and this N here should be the same K and N that should be appearing in here because we're talking of the same reaction. So if I will use the K that I have here, my rate expression or my rate of reaction for the concentration, which is 10 moles per liter, should be equal to, so you have the K, you copy the K that you have here. This K is 0.2 over 1 raised to N. By the way, if 1 is raised to any value, what would be the answer of 1? As long as N, by the way, class, this N here, this order of the reaction, as learned, as discussed in kinetics of homogeneous reaction, it could be a positive whole number, it could be a negative whole number, it could be a fraction, it could be a decimal. So it could be any real number. What happens if you process 1, let's say cube root of 1, square root of 1, 1 raised to 1 million, or 1 raised to 2/3? What's the answer? Like this one, I'm talking about this.
One, miss.
Oh, 1, correct. So the answer is still 1 because it's 1. Anything you do with it in terms of raising it to a particular exponent, the answer of this, by the way, this one would always be 1. So a 0.2 over 1 raised to n is actually a 0.2, right? So I will simplify this. This would be a 0.2. The value of the n in this case is immaterial because any exponent of the 1 will be equal to 1. So in that case, I'll place here a 0.2 for the k. Is that okay? Is that okay if I write a 0.2 for the k in here?
Yes, Miss.
Oh, right. So it's okay because this k and this k are just the same k. We're talking of the same reaction. So I will write here 0.2. Then your Ca is 10 raised to n. So in this case, class, your answer is an expression. You cannot answer an actual value just like the one I gave in the quiz. In kinetics, it's not always that you're going to answer with an actual specific value or quantity or a numeric value. It could be an expression that is asked from you, especially if the information provided by the problem is not complete. So in this case, the rate based on the second concentration is 0.210 raised to n. It's dependent on n because in the first place, the problem is saying that n is not given. So it depends on the n. If the problem will say n is equal to 2, then you just have to place in here 2. Then you will have the corresponding rate of reaction. Do you get it? So your answer will be this. Your answer is an expression, not a specific quantity or value. Any question before we go to the next example? Okay, none. So we will proceed with what we have here on Lebenspiel. Okay. I would like to look for a problem somewhere here which directly use the formulas that we have discussed. That way you will have something to refer to. Okay, I'd like to use this one, the 3.29 and the 3.30, because this one uses the, I think the concept, or will be using the concept that we have just discussed. I will just take a picture of this so I will not have to go back to this part so I can continuously share. Okay, I'll go back to the whiteboard and process this too. So I will read the problem, that way it's clear to you what is provided in these two problems that we have. Okay, let me just check. So for the first one, that's problem 3.29. Find the first order rate constant for the disappearance of A in the gas reaction 2A forming R. If on holding the pressure constant, the volume of the reaction mixture starting with 80% A decreases by 20% in 3 minutes. Oh, the problem here, class, is there's already a change in the volume. So this is variable volume. We cannot answer this. So I will just not use this one. Okay, we'll have the other one. Find the first order rate constant of the disappearance of A. Oh, okay. So these two are all gas phase reactions. Gas phase reactions are not all the time constant volume, but rather at most of the time they are variable volume. So we cannot use this particular problems as a sample. We'll look for another set here. Okay, there's a change in the volume and we're not yet with that. We have not yet discussed that. So let's check whether we will have something here. This one is reversible, so we have not discussed that yet. Okay, we say, okay, we can try with this 3.2, 3.3, 3.4. Let me just check. Take a picture. Okay, let's go to our whiteboard. So if it's 1:30, we transfer to the other link. Okay. 3.2. A liquid, or specifically liquid A, decomposes by first order kinetics. So I'd like to write down what information I can extract out of that statement. So we have the liquid decomposition of A by first order kinetics. So since it's first order, my N is already equal to 1. So I can write it down. And it's in a batch reactor, and 50% of A is converted in a 5-minute run. So do you have this information? 50% of A, so meaning your XA is 0.5, for T equal to 5 minutes. Okay, for a 5-minute run, 50% of A was converted. Okay, how much longer will it take to reach 75% conversion? So I will have here T for XA equal to 0.75. Okay, so you have this given. So again, we will read the information. So I will read it again. Liquid A decomposes by first order kinetics in the batch reactor with 50% of A converted in 5 minutes. How much longer would it take to reach 75% conversion? So based on what I have read, these are the information that we can single out from the problem. Now we'll go to the solution. What do you think is the appropriate equation to use here since the problem is talking about conversion? So it's giving of conversion here for a given time, and then it's asking for the time for this given conversion. So what do you think is the appropriate formula to use? First order. So first order reaction, would this be the appropriate formula to use? The negative ln of 1 minus xa being equal to kt. That's for first order. This is for first order unimolecular type of reaction. So this is the first formula. The other formula is this. So this would be the formula that we will use, okay? So I'm just showing it to you so you would recall. So we'll be using the formula negative ln of 1 minus xa being equal to kt. The purpose of this first set of data is for you to be able to know the rate constant. We know already that this is the formula that we're going to use because the problem already gave us the order of the reaction. So all you have to do is substitute. So negative ln of 1 minus 0.5 is equal to k times 5 minutes. So you will have a rate constant here, since this is first order, having a unit of per minute. What is the answer?
0.1386 per minute, Miss.
Oh, thank you. So you have 0.1386 per minute. Now, this is the same rate constant that you will use here on the same formula for the requirement here. The time it would take for 75% to be converted. So negative ln of 1 minus 0.75 is equal to 0.1386. Okay, and you will have the time. This 0.1386 is the K that we substituted in there. So we have the ln of 0.25. That would be negative. It's a negative, so that would be positive. So your answer would be 10 minutes. So after 10 minutes, or 10.0021, 75% of A is already converted. Okay? So that's a sample of a problem that uses the formula that was derived already. If you're not going to use it in testing a given set of empirical equation. Okay, so we'll go to our go back to Levenspiel again. Oh, sorry, why did I go back? I already took the picture. So we go now to the second. Repeat the previous problem for second order kinetics. So for second order kinetics, same information. N is equal to 2. We'll go to this one. So this time you will have N equal to 2. You have XA being equal to 0.5 at T equal to, what's the time there? 5 minutes. And you will have the time for XA equal to 0.75. Okay, the order of the reaction is second order and we only have species A. So based on what we have discussed in the 3 cases of second order reaction, which of the 2 cases will we use? We are given A as our species. We're given a second order reaction. So what will be our formula to use? Will it be this one? Or will it be this one? Or will it be case 3? So you just say case 1, case 2, case 3. Or we can have case 2 or we can have case 3. The thing is, I will just take out of the picture case 3 because that's for a non-elementary reaction. Okay? Now we will only have case 1 and case 2 to consider. Actually, automatically, you should know which of the 3 cases will be applicable in this case. What do you think will be the applicable scenario here? Case 1, case 2, or case 3? Or
Case
if
2, Miss.
Case 2, Miss.
so, why case 2? So, hindi pwede. Gid yung case 3, no? Kay ano?
Kay isa lang yung reaction species, Miss.
Correct. Very good, Socrates to. Sige, so since you only have one species, so case 1 kag case 2, out of the picture na kay duwa ni ka species, yang iya gina-istorya. So we go back to case 2. So case 1 and case 3 not applicable anymore, and this is your formula. So I will just use this one. I will use this one. Why will I use this one? Because the problem gives us conversion. Okay, so I'll go back to my whiteboard. So I will have, so in here, case 2. Case 2, it's case 2. You have 1 over CaO, XA, 1 minus XA equal to KT. This is our formula. So if we will use the first set of information, this one, so I will keep this one here. I'll transfer the CaO on the other side. I will have 0.5 over 1 minus 0.5, and I will have K CaO and a time which is 5 minutes. You need not worry again that the problem is not providing you with this, because anyway, CaO is a constant. The initial concentration is a constant, just like your rate constant. So you can apply this particular equivalent expression to case now wherein conversion is 0.75. So you have a 0.5 here over a 0.5, that would be 1 over 5, that would be 0.2. So the value of your KCAO is equal to 0.2. Correct me if I'm wrong. So I will now use the second scenario. Then I will use this formula. So for a scenario wherein conversion is 75, so I will have 0.75. 1 minus 0.75 is equal to, this KCAO will be 0.2. So that would be 0.2 T. So now you have the time for conversion of, for 75% conversion on a second order reaction. So it's 0.75 divided by 0.25 divided by 0.2. So your answer is 15 minutes. So it will take a lot longer for a second order reaction to reach 75% conversion, because sa first order reaction, it's only 10 minutes. But if it's a second order reaction, that would be 15 minutes. Do you get it? Questions? Okay, let me check what we have there. I'll go back to here so I can show to you what problem we can use. So 3.4 is talking about a 10-minute experimental run that shows that 75% of liquid reactant is converted to product by a 1/2 order rate. What should be the fraction converted in a half-hour run? So this particular problem will require that you set up your own differential equation or your rate law, because the order of the reaction is 1/2. It's not 1, it's not 2, it's not 3. So you have to set up your own rate expression. So we will have a 5-minute breather. I will stop here for now. Stop sharing. And then we use the second link that I have provided.